Welcome back. In this lecture, we'll start with the Reynolds average Navier-Stokes equation, and then we'll learn that how, after adding this new variable tau r, which is the Reynolds stress, how we can use different models to estimate this particular variable using the flow variables. We know that this tau r, which is the Reynolds stress, is equal to negative of rho times this particular tensor, which is nothing but the Reynolds strain rate, and in the Einstein's notation we can write this as negative of rho times ui prime uj prime and the Reynolds average of this. So one of the hypotheses to estimate this particular strain rate is Boussinesq hypothesis, which we discussed in our last lecture. So in this lecture we will see that how we can use a very simple model to estimate this particular rate of strain. Now let's first put this particular equation in the original equation. So we'll get here this P star is the new pressure, which is nothing but the averaged pressure plus this term which comes from this additional term which was there in the Boussinesq hypothesis, and the other term is added to the viscous term. So you can see here, and this term is nothing but this. Now in the zero equation model we use a analytical relation. So in an analytical relation we estimate this turbulent viscosity using this particular equation, so which is called Prandtl model. In this model, the turbulent viscosity is estimated using this times dou u bar by dou y, where Lm is equal to kappa times y, where kappa is von Karman constant equal to 0.41 and y is the distance to the nearest wall. Clearly, in this particular model, we have the distance to the nearest wall involved. So therefore, this model is recommended for those kind of flow where the flow is wall bounded. There is a wall and you are interested in finding out the boundary layer behavior of the growth of the boundary layer in this particular flow. So in a free shear flow, this particular model is not recommended. In order to solve any fluid flow in OpenFOAM using zero equation model, you have to write your own piece of code, write your analytical equation such that you can manipulate the turbulent viscosity, ultimately the viscosity of the flow. Since this is pretty much involved, we are not going to do this in this particular course. We'll stop here for now, and in the next lecture we'll talk about one equation model, and we'll also use that particular model to simulate flows using OpenFOAM.